Okay, let's get started. So today, our main topic will be on metric elicitation. And the goal is to tie it to both some of what we've talked about already, but also a bit future-facing, depending a little bit on time, but I suspect we'll get through enough that we'll get to some of this. I plan to touch on one of the topics that ties metric elicitation to mechanism design, which is something that is sort of coming up quite a bit later in the class. Okay, so far we've talked about, last lecture was active learning. So we were trying to understand, mostly the idea was we can frame many preference elicitation or preference selection tests as machine learning problems, essentially classification ranking problems. The first lecture essentially tried to make that claim. Up to, again, a lot of caveats that we've pointed out over the subsequent classes, right? So we posited a point of view, this sort of utility maximization type perspective, tied with sort of Boltzmann style utility functions. So these are like functions that are the key normative claim, just to give a summary, because I'm attempting to read faces on where people are. So summary from beginning of class, interested in preference modeling, posited that one of the primary ways of thinking about this problem is to frame everything as sort of a utility estimation and then sort of preference selection kind of methodology. So the key idea here is that you think of choices as being governed by some underlying utility, and we build models that can help us estimate these. And we showed in the second class actually, that all these things boil down to essentially a kind of machine learning problem, where we're essentially turning preference choices, which can be the sort of binary or ranked choices or other kinds of comparison choices, into classification problems. And so this looks like machine learning. And so, again, it's somewhat of a narrow view, but it is the predominant view, and a lot of work has been built around it. And over the next couple of lectures, one of the things we did was trying to expand that perspective to include sort of multi-stakeholder perspectives and a bunch of other things that may be missing from the narrow utilitarian framing of the problem. So that's where we were. In the last lecture, we tried to connect this to active learning. This is the idea that in machine learning broadly, we found a lot of benefits in framing various kinds of learning problems as active learning problems. The idea here is that instead of having nature give you the samples that you're going to label, you have a procedure that explicitly seeks which examples need labeling. And the claim is that if you do this intelligently and sort of your world is sufficiently structured the right way, I can learn much faster using this than using sort of standard existing, just like found data style labeling. So random data labeling can be less efficient in terms of, in this case, we called it sort of sample complexity effectively, or query complexity. This has come up again here. How many samples do I need to be labeled in order to do a good job of the learning problem? And in the last class, what we tried to do was sort of discuss active learning as an interesting idea and then connect it to preference learning, saying that a lot of what we know about active learning can be applied to preference learning. And we showed some examples, for instance, in the sort of car navigation example, to show that these two tools combined can actually be quite valuable in lots of real world settings. So that's where we are today. So today we're going to extend. Any questions on general framing? Yes.
So from the last class with Stanford, active learning is for like collecting library data sets, but not necessarily, active learning is not necessarily the utility maximization function.
Yeah, so active learning is a generic procedure for, but it can be applied to preference learning. And so part of what we're hoping to pitch maybe is that one of the gaps that seems to exist in the preference learning literature is active learning as a way to help it be more efficient. I'll give a stronger argument today, or at least a argument today. Well, I can actually just mention how. So one of the reasons that active learning is appealing in a preference learning setting is that, remember, the key task in learning from human preferences is asking humans questions. And we've done a little bit of work talking about literature. Maybe actually this question suggests maybe we should actually anchor on this a bit more. But there is literature, and maybe just anecdotally, it's not maybe hard to argue that people get bored very quickly, right? And so being very efficient and trying to get examples from people can be a good thing, because this means that you don't need to ask as many questions to learn your utility function. So the way these things connect is if you're interested in sort of getting samples from people as a way to learn their preference function, and as a maybe normative or at least observational claim, sample collection from people is fraught because people get tired and maybe expensive, and so you want to make this very efficient. And combining this with tools that we know for like active learning to help you speed up learning is a sort of good combination. That's the overall. Okay. So we're going to play with the same kind of ideas today as last time. The difference here, so the main difference here is that instead of thinking about the utility estimation problem in a generic sense, I'm going to narrow down to a sub area where there's been a meaningful amount of work that I think is interesting. So interestingness is maybe the first order motive for presenting this. I think it has some lessons that are potentially useful for more broadly framing some of the questions on sort of preference elicitation. Specifically, instead of thinking about sort of this active learning elicitation, preference learning problem in a generic sense, I'm going to narrow down to the specific setting of picking metrics for classification problems. So cost-sensitive metrics for classification problems, which is a sort of narrow version of this broader set of things that we're interested in. In this case, the utility that you're looking to elicit are the relative trade-offs. So say a different cost that people might have for different kinds of cost-sensitive classification problems. And so most of the class today would be on this narrow, like a deep dive on this version of the problem. And the connection to previous lectures is it's again a sort of preference elicitation problem, but again a special case. And we'll be using the active learning sort of point of view. So we'll be very sensitive to number of times you ask a question, and that'll be sort of one of the main criteria of success. And one nice thing is that we'll be working in settings where you can quantify this, which is not always true. So, many of the big problems that we're most interested in sort of modern machine learning, explicitly quantifying how many queries you need to actually get a good answer. So sort of this active learning problem plus quantifying the query complexity is a hard problem. I don't know how to do this for RLHF as a specific statement. But in settings like what we'll cover today, there is work. You can actually give bounds, for instance, and quantify how many samples you need to answer these kinds of questions. Okay. So we won't go into proofs. We'll state some very simple theorems when they're around, and I'll refer to papers for details. Other questions on framing, setup? Yes?
It's like a simple example of a classification.
Sure. So I'll go through that in a second. It's good. Good question. It's, in fact, the next question. The next slide. So the setup for this problem is that I'm interested in building, let's say, sort of a simple classification model. So the mental model you want to have now is that, or maybe I can ground this. A lot of this ends up being very useful in, say, clinical decision-making. For a variety of reasons, in general, in most machine learning problems in the real world, different kinds of errors have a different real-world cost, if you like. Right? So I'm building a classifier. Perhaps what I care about is the actual literal number of mistakes the classifier makes. So that's my major metric of interest, and I care about accuracy. Fraction of errors, right, as you know. Or maybe false positives are really expensive. So predicting a label, an outcome of positive when the true outcome is negative. In a medical setting, maybe this means that I incorrectly diagnose a cancer, I incorrectly state a cancer diagnosis. So this, of course, causes lots of harm to the patient, as you might imagine. Incorrect diagnosis of any kind. And of course, as you might know, in medical decision-making, trying to understand better error rates of different tools of different kinds. And so not just that it makes an error, but the specific kind of error actually matters. And so one of the ways to frame this question in learning setting is to think about sort of coming up or thinking through sort of the right choice of metric that's most relevant for the task. And so you might think about this as picking one of these statistics or thinking about mixing some of these statistics, like weighted averages is another way to think about this. So I'm much more sensitive. An example is I'm much more sensitive to false positives and false negatives. And so I want to weight in my learning problem sort of pay much more attention to errors of false positive kinds of errors, so incorrectly making, say, incorrectly making diagnoses of a particular condition versus maybe false negatives. May or may not be true. I'm just stating that in many settings, errors are asymmetric. Like they don't cost the same, different kinds of mistakes that a model can make. And so they don't cost the same. One way to build this into the model is to come up with some measure that sort of captures the asymmetric costs of different kinds of mistakes. In classification problems, this boils down to binary classification, though many of these things can be extended to other kinds of learning problems. In this lecture, we'll mostly do the binary classification case because it's succinct and sort of easy to explain. And I'll try to give some detail where helpful. So here, there are only two kinds of decisions that a model might make. It might make a positive or a negative decision. Those are the only two choices in a binary classification problem, as you know. And then there are only two states of the world for every example. It's either sort of correct, or positive or negative. And so the measures of incorrectness are, did I state that something was positive but was actually negative or zero, depending on how you just label things? Or did I incorrectly state that something was, did I predict negative but the true thing was positive? So either way is a mistake. And the claim here is that when the costs of mistakes are asymmetric, then building in tools, one way to, that the sort of human preferences are helpful here, or preferences might be helpful here, are helping to ground asymmetric costs of different kinds of mistakes. Okay. So, I built some model. It has a high accuracy. It has maybe 90% false positive rate, 5% false negative rate. If I'm sensitive to accuracy, so overall performance, then, this is a good model. Perhaps this is quite bad in terms of false positives. There are lots of reasons why this can happen. Some of it could be tied to the overall prevalence in the population. So sometimes that is part of the skew. Here's a model. Here are some statistics. The key claim here is for the same model, there are different ways to measure error. And here's at least three. Right? And each of these three could be the right answer or some combination of them for different settings. So I pick another model. Here, this is an illustration of, say, a nearest neighbor model, for instance. Right? So it's a different learning model, same data set, same problem setting. It has a different accuracy. So perhaps here it has a lower accuracy, 89%. Right? So it's worse in terms of overall performance. But in false positive, it's better. So it went from 90 to 50. And in false negatives, also better. So again, these are real numbers from a real problem, by the way. So I can reverse engineer. I have a spreadsheet somewhere. I can reverse engineer some of these. They actually make sense if you look at different rates of different kinds. Again, often prevalence makes a big difference. And then I would say a third model. In this case, an illustration of support vector machine. So different accuracy number, different false positive number, different false negative number. And so the decision for you as a designer here is I need to pick a model. I've explored three families of models. I've fit all my models the way I like to. I'm in some decision-making setting. I have three different measures of good performance, right? Which capture different things, right? Overall performance, false positive errors, false negative errors. I need to make a choice. Thoughts on which model I should pick and what might guide a decision. I've given some of this away, I guess, in the discussion, but question for the group. So, if you're faced with this as a designer, which model would you pick and why? And maybe what might move your decision?
I think if it's in a medical application, I'd pick the second model because I'd want to have as little false negatives as possible.
Okay, so that's probably a reasonable way to think about a decision. Anyone else? I think default for most of us is accuracy. I think that's what everyone just looks at. You may not even bother looking at the other metrics. Anyone want to fight for false negatives? Maybe some setting where that might matter.
The case of cancer prediction that you mentioned.
Yeah, it's missing something.
False positives as least and false negatives can be they're okay with that matrix. complex. So maybe I'll go with the set mode rectification.
Yeah, perhaps. So, maybe you're okay with overdiagnosis, for instance. So, again, it depends on context. Go ahead.
This is another context. I can think that in the criminal justice system, you don't want to falsely incarcerate somebody.
Indeed.
So,
That's a great example.
False positives are bad.
Yeah. So, again, just repeating a bit. So if you're using these kinds of models as part of decision support and say recidivism, which is a common use case, it'll come up later actually, then they're incorrectly accusing or making some claim about sort of potential, for in that context for sure, like incorrect predictions, over prediction is a big problem. That's something you'd be quite worried about. So you want to be conservative in a different direction in that setting. So what is hopefully clear from this slide is, again, even in this very narrow setting that many of you are, again, almost everyone here is taking a machine learning course. You're very familiar with this. The main thing I'm hoping to highlight is that even here, choosing the, if you like, utility function, cost function, loss function is actually not a free choice. We often think about it as a free choice. We don't think about this carefully often. This whole class has been about much more complicated settings where we think about choosing utilities or reward functions. So how do I choose a reward function to measure language model performance or measure funniness? As I think was one of our first examples. These are for sure complex, complicated things. But even in what we might think of as a simple thing, like I just want to build a binary classifier, the argument here is that evaluation choices can be complicated and contextual and depend on sort of the application setting that you're interested in. And so almost always, or maybe as a strong claim sort of across most of learning, choices of evaluation or utility functions can be as important as every other choice that you're making in your model design, because they can completely change what you value, what you think of as sort of a good result. So somewhat underappreciated, but for it's the premise of the work I'm going to talk about today. So useful to highlight. Okay, questions, thoughts? Okay, so it boils down to this choice of how you measure performance of a model, and one argument, and the main argument in the discussion today is, the actual thing that you end up picking is some performance metric, which is some quantitative description of how you are evaluating errors in your model. Again, similar equivalents, essentially a sort of, from the point of view of this class, reward, utility, metric roughly mean the same thing. It's just mostly different domains have picked different sort of specifications, but from our point of view, these are all similar things, but some description, some quantitative measure of goodness of whatever procedure you're building or whatever machine learning model you're building. And so your argument here is, as discussed, the choice depends on relative costs and benefits and might change depending on how you choose to quantify relative cost and benefit. So, so far we've talked about these as maybe three options, accuracy, false negative only, false positive only. You can also think about these as weighted combinations, and that ends up often being very useful, meaning the relative, not in terms of an absolute binary, I'm picking one of these, but actually how sort of much more expensive is a false positive error than a false negative error. And if I can quantify this, then I can give a weight to these different kinds of mistakes. And I can think of building models that optimize some weighted combination of the different errors that a model can make. In this case, errors the model can make are different kinds of classification errors. So two types, false positive, false negative. If you don't like errors, you can go different kinds of correct predictions the model can make. We'll go through this in a second. Same kind of idea. So you can think of true positives and true negatives. So did I correctly predict negative, and did I correctly predict the positive? Turns out that these are essentially equivalent. We might go into this if we need to today. Okay, so a bunch of different metrics out there. Even within classification, even within binary classification, we went through at least three. If I expand to sort of different kinds of learning problems, there are a ton of them across lots of different learning problems. Even if I stick with binary classification, If I allow myself to do weighted combinations, I've immediately now gone from, say, 3 common options to really infinite options, because all weightings, so all real valued weightings are valid choices of measures that make sense in this context. So very quickly, the space explodes, even in this very simple setting, not to talk about, again, more complicated settings we've talked about in class so far. Another useful argument, again, this ties to a lot of discussion in class today, but I find it valuable even in this simpler setting because, again, there's this implicit assumption in many learning problems that sort of any metric is as good as any other metric. And so I can just sort of, maybe the actual answer is different, but, things should relatively order models the same way. And so just pick any of the metrics and they should all behave sufficiently similarly that any metric is as good as any other one for any of the things that we need to use them for in machine learning. So again, for selecting models once I've trained them, or if I have a metric, I can convert that into a loss function that I can then actually directly optimize. So are they exchangeable or not? So there are lots of examples showing this is not true. Here's one of my favorites, because it's salient for, I guess, when I was a PhD student. I think this was one of, for me, at least at the time, quite striking as an example of where metrics can fail. So any of you know the Netflix prize? Okay, it's still around. Okay, so I guess Netflix is still around, so it's good. In the 2010s, when I was a student, or was it around that? I think it was earlier than this. But anyways, there was a lot of excitement about academics and industry broadly trying to improve on Netflix's recommendation system algorithm. And so they created this prize where they sent out sort of a large data set of sort of existing recommendations and asked people to predict missing recommendations. And so this was a competition. They had a prize tied to this. It was $1 million. It's a huge amount at the time. Probably even now, sort of a big deal as a prize for this kind of competition. And it ran, I believe it was a year. Though that's checkable. I don't remember anymore. But I tried. We didn't do that well. We did okay, but not that well. But lots of teams built tools for this. If I remember correctly, this team was at least the leads of the winning team that deployed the algorithm. There's also other color I could mention offline, but I'll just tell the main story here. The metric they chose to use was what is the root mean square error of the prediction of the actual rating number. So in Netflix, as you might know, you get to rank things 1 through 5 stars. So for every user, for every movie, if they've rated the movie, there's a number, 1 through 5. And what Netflix chose to measure in the competition was mean square error, average of the squared error difference between whatever prediction you gave for the rating and the actual 1 through 5 number, and then square root over the whole thing. So RMSE. Is that clear? Actually, the details don't matter. So it's a choice of number. But what they actually wanted was to improve the recommendation algorithms. And arguably, what matters for recommendation, if you think of your Netflix interface, is mostly like if I get the top of the ranking correct. So I want to get the first 5 or so to be things that you're likely to say you like, because that's what you see when you turn on Netflix. Is sort of a dashboard, but people, as you might know, there's a strong bias to the top of the list. So you want to get the sort of top few things likely accurate, so people are likely to click on it, and hopefully likely to like it. But it's sort of confounded a little bit. Click on and like is sort of assumed to be very close. And what they found was that predicting root mean square error as the measure did not necessarily correlate with trying to do a good job in terms of actually getting top-end ranking. And in particular, you could come up with very naive algorithms, something very simple like a PCA thing or just like overall popularity, often did much better than some of the methods that came out of this competition. Now, the competition made sense in its own context. It was trying to optimize for root mean square error. And from that point of view, they got some good algorithms. But in terms of the actual task, it turned out that they didn't pick the right metric. And in fact, there were other metrics that made a lot more sense. There are lots of metrics for top-end ranking, particularly, that would have been better suited, that if they had picked, they might have gotten models that were sort of better suited for the task that they cared about. And so, for me, this was a very salient example of sort of coming up with a task, picking a metric that on its face sounds extremely reasonable. It's going to look for like average error. We use squared loss all the time. RMSE is a small variance of squared loss. It sort of sounds very reasonable, but it actually is a bad idea. And methods that win in respect to this metric are actually often, the argument here was that they're often not useful for the actual task that this was meant to build. So another example of, again, metrics can matter a lot in terms of building algorithms. As a fun side anecdote, it turned out, some of you might know this, that Netflix did not actually end up using any of the winning competitors. Does anyone know why, if you know some of the history? So some of it is this, though I think that's not the biggest thing. Something else. It's another fun part of, I guess, norms in maybe academia and industry.
What year was the competition?
If my memory is correct, I think this was in the end year, so I think 2010. So it wasn't a deep learning.
Oh.
So it wasn't, that would be interesting. I think they were using a matrix factorization type method. They had been using that and some other sort of content-based thing. That was their previous thing. So the short answer is, it turned out, the field came up with, this is the heyday of very fun, sophisticated matrix factorization methods. There were lots of sort of Bayesian hierarchical methods and things like that. It turned out that they were very expensive to run. They couldn't be run in production settings at the time, at that level of compute that people were investing. And the method that they were building, that they had internally, sort of was as good in terms of the things that actually mattered, but much less compute intensive. So another fun side anecdote. They ended up not being useful to them. It was great press, though. I think I think more than, I don't think academics paid, I think they got more than $1 million worth of effort of people who were researching them, of being able to, get people to come work for them. There's a bunch of other stuff that they probably got out of it. But the actual thing they thought they would get, they did not get. It's a fun anecdote.
Okay, so what's the real lesson then?
The real world lesson?
Yeah.
Oh, this is what I care about. This is the lesson for the class.
Compute.
Well, okay, so my counter, so the argument is it's only compute because I guess your argument is if they had enough compute, they would have run whatever won the competition. The counter is whatever won the competition was good on RMSE, and I'm saying it wasn't good necessarily for what they cared about. So the whole premise of this is it's not just compute. Under the assumption that sort of the world is not perfectly predictable, which I think most of us hopefully will agree that there's always noise. And so relative costs, relative errors do matter, and quantifying it appropriately for the task can make a big difference. Another example, this comes from fairness work, but I think is another salient example. So this is tied to, we're talking about legal type applications. This is recidivism prediction. So this is risk of reoffense. This is work out of, I guess the company was called NorthPoint. The algorithm is called Compass. I think it's still around and still in use, if I remember this correctly. But the goal was it was supposed to predict the risk of reoffense, which should help a judge in sentencing decisions. And so NorthPoint was interested in good performance, accuracy, but they're also sensitive to some notion of fairness. So how does this treat different demographic groups? And so in particular, they used a notion of fairness tied to calibration, which is roughly asking for different sort of probability bins of risk, they should be reasonably well calibrated across, tautology. They should be similar across different demographic groups. That's what they were hoping to capture. There was a post-analysis by ProPublica, which is a media company. And what they did was they looked at a different metric. So they looked at false negative rates and false positive rates, which is sometimes called equal opportunity in the fairness literature. I may get that wrong. The acronym is EO, but there are actually two metrics that are called EO, and I sometimes mess it up. But I'm happy to send a reference. Anyways, so false negative rates and false positive rate differences across demographic groups is the actual technical thing that we're looking at. And what they found was that black defendants were twice as likely to be incorrectly labeled as higher risk than white defendants, and similar kinds of issues if I looked at the other. So if I looked at false negative, I saw, again, big disparities. False positive, I saw big disparities. So again, from is this a good algorithm that sort of normatively a good thing we'd like to deploy? This was worrying. For me, the salient takeaway from this work is, it wasn't, the claim that the Compass algorithm was not sensitive to fairness issues is incorrect. Like, they actually had a fairness notion. They built something. There was a different party that post-studied their algorithm, but used a different measure and came with completely different conclusions, right? And the argument here is, again, two quote-unquote maybe well-meaning actors who are building algorithms can have different normative views of what might be sort of a good outcome for an algorithm. From different normative views, they pick different measures and actually completely disagree in sort of how they evaluate a particular algorithm. One actor says, well, I've done what I said I was going to do. I've built a fair algorithm for this very sensitive societal decision-making task. Someone else is an auditor. They look at the same task. They look at the same results, but they use a different measure of performance, or in this case, a measure of fairness. They come up with a completely different conclusion. This led to, I think there's also maybe a fun anecdote on this as well. This led to quite interesting academic work, actually, where at the time there was some hope, I think also maybe a bit of naivety in the technical fairness community, thinking that we could come up with some measure that was like the golden measure. So there exists some metric that will be fair in a universal way for all different settings. And I think people didn't appreciate that, again, as the premise of this class, the actual metric you select has a big influence. Till this article, because it made a big splash. I mean, some splash externally, but I think meaningfully bigger splash actually within the technical community that was studying this, because it really anchored the problem and led some follow-on work. If you've ever heard of impossibility results in fairness, it comes from sort of the prompt of this work led to people to study this much more carefully. And the main conclusion was sort of, if I'm interested in binary classification problems with sort of fairness measures, roughly you can pick one, maybe two measures to sort of try to maximize at the same time, but you can't pick three. So the simple way of saying it is, there's no universality. Different metrics will optimize, different metrics will pick different things as sort of the fair outcome. Or if you want to think about this in a sort of pure metric selection sense, the degrees of freedom are such that once I pick multiple measures of fairness, I will not satisfy all of them simultaneously. Some of them will break. So another example of the same phenomenon. Okay, so one of the ways that at this time my group was interested in this question, so one of the ways that we chose to engage in this question is to ask whether we could use human stakeholders, this is, again, the premise of this class, as a way to select metrics that align with the preference of whoever the stakeholders are. So the idea was there is not a right answer, but perhaps for particular stakeholders, there's a right answer for them. And so can we come up with an algorithmic tool that helps them efficiently select the metric that best aligns with their preferences? That was the premise of this kind of work. And so this led to what we ended up calling metric elicitation, which I'll go through in at least the high-level key points over the next couple of slides. Okay, so it's related to a bunch of other stuff, some of what we've covered already, some of what we'll talk about later. So we haven't talked that much about bandits yet, but we will. So it's related to some of those ideas. We've talked a little bit about inverse reinforcement learning, but we connected some of those. And there's some sort of older core literature in, say, psychology, econometrics that thinks about elicitation, which I think for the purposes of this class is reasonable to think of as, again, this combination of utility estimation with active learning is a very good summary of it. Okay. And again, we're interested in this sort of narrow special case of using this as a way to pick good classification metrics, or metrics tied to classification models. So I'll mostly talk about the simple case of binary classification metrics. I'll refer to papers if you're interested to sort of other settings that are like the fairness setting, multi-class setting, there's a bunch of other settings that you could use this. So you can show that sort of binary classification metrics, linear binary classification metrics, can all be reduced to something that looks like this. So as I alluded to earlier, you can think about this in terms of errors. So there are two kinds of errors a model can make: false positive, false negatives. It's a binary classification metric. And so you can think about this as like the relative weight of false positive errors versus false negative errors. And so the problem that you're trying to solve, if you're trying to elicit a linear binary classification metric, is to fix a number for A1 and A2. As an aside, it turns out scale doesn't matter. This is the same thing as, or let me say this better. We can't recover scale. Also, scale doesn't matter, actually. Meaning, if I scale this thing up or down, it's the same metric. It picks the same classifiers. It ranks things the same way. So it's sort of invariant to monotonic transformations, actually. A few other things. So the way that this shows up here is that actually it's not really two numbers. It's really, the numbers are a bit tight together relative to, you can scale them up so that they sum to 1, for instance. So if you pick, there exists a rewriting of this where I can pick an alpha and 1 minus alpha as the relative weight. It's the same problem. So I need to pick a number which tells me the relative weights on two different kinds of errors as a population measure of a classifier. And if I can pick those numbers well, this addresses the sort of relative cost of errors for a binary classification problem and is useful for sort of trying to solve this kind of problem. Questions on the setup? Okay. So I'll mostly discuss the noise resetting because I think it's, or at least I'll start off with noise resetting because I think it's probably the easiest, and the algorithmic tool will be sort of straightforward. And perhaps I'll mention some extensions to other settings as well. So I already mentioned some of this, but if you're interested in binary classification problems, at least in terms of population performance, overall performance across the model, the way we quantify errors are, again, these 4 numbers, right? So it's sort of true positive, true negative. True positive is a fraction of times the ground truth is 1, the model predicts 1. True negative, fraction of times ground truth is 0, model predicts 0. False positive, false negatives are the two kinds of errors the model is making. So is it making a mistake and incorrectly predicting 1 when the ground truth is 0? And how often is this happening? And aggregate across the population. And then false negative errors, is it incorrectly predicting zeros when the ground truth is 1? And then you're aggregating this across the population. Okay, so this is called the confusion matrix for binary classification. You can extend this to confusion matrices to multi-class classification. Instead of doing this for just 2 classes, I have all K classes that are possible ground truth, all K classes that are possible predictions, and I have a K by K matrix for all possible combinations of sort of ground truth and predictions. And typically, those don't have a name within the box. It turns out we do binary a ton, and so we can call them specific names. But you just have, I guess, generic confusion matrix for larger multi-class classification settings. Is that clear, by the way? I don't know if I have a K-class problem. I would just have a K by K box, right, for y equals 1, y equals K, and then my predictor equals 1, my predictor equals K, and I'll count the fraction of times. Like each of my examples falls in any one of the buckets, and I get a K by K confusion matrix. Okay, and then linear, so you can also show, this is going to be a fun aside, we won't go into too much detail, but you can also show that most classification metrics that people use or you might be familiar with can be written as some function of the confusion matrix. It turns out to be a useful quantity. And so in particular for linear ones, for binary ones, you can think of the composition function as just a weighted sum on, in this case, the off-diagonal. So it's some number that multiplies the false positive number, another number that multiplies false negative. Again, there's some degrees of freedom that you have to play with. But linear metrics can be written as, again, just these 2 numbers, picking these 2 numbers. Okay, so a little bit on algorithm. So before presenting the algorithm, it's useful to do a little bit of discussion. So I'll spend, I think, 2 minutes on this. Does anyone know, so if I'm interested in the best classifier that maximizes expected value of my data over my data. So x, y. Think of this as a distribution of the accuracy. So indicator h of x equals y. If I know my distribution, does anyone know what the optimal classifier is? You might remember this from. Anyone want to guess? So I know my distribution, I know my p of y, p of x, p of y given x, all that stuff. You know the answer to what model choice, if I knew my distribution, and I could pick any classifier, including one tied to my distribution, which model should I pick that maximizes accuracy? Similarly, minimizes errors. So I can rewrite this as minimum over h, the number of times I make a mistake. Same exact problem. Then I'll remember. You've almost definitely seen it before. Anyone want to guess? So it'll be something in terms of the probabilities. So this might be a fun exercise offline. You've definitely seen it before, or I suspect you've seen it before. When you build a logistic regression model, so logistic regression gives you a probability, p of y given x. How do I convert it into a decision? Yeah, so you pick a threshold. There's a quote-unquote natural threshold that everyone uses. Okay, so it turns out that if I know my population, is actually the reason why we pick a threshold half for a logistic regression problem. And you can trace some of this in the technical literature as well. It turns out that the optimal decision-making rule is choose one if p of y given x is greater than half, or 0 otherwise. This is like the optimal classifier to choose. You can also write it as, sometimes people write this as sine of p of y given x. Sorry, I should rewrite this. It's a minor thing, but it can be important. So typically we use the positive probability, y equals 1 given x greater than equal to half. So this is the same thing. I sort of subtract out a half, check if it's greater or less than the threshold. If it's 1, I pick 1, otherwise I pick 0. Negative 1 is the same thing. Okay, so you might have seen this. This is sort of somewhere logistic regression semantics come from. The idea is that we hope logistic regression gets us this, and then we can threshold it appropriately, and we get sort of good classifier. What happens if I go from this problem to a weighted problem? So I'm going to write it in these semantics, and to make it closer, I want to make this, instead of accuracy, I want to make this error. I'd make this minimum of number of mistakes. And so suppose I wanted to solve a different problem, which is min over h, keep my expectation over population. And now I'm going to look at two different kinds of errors. So this is h of x. I have false positives, so I predict a positive, but y equals 0. Plus the other kind of mistake, h of x equals 0, y equals 1. Okay, so this is my overall problem. And suppose this is the exact same thing as this, because this is the two ways I can make a mistake. So I'm just decomposing that. But suppose I have a weighted version. So I put an alpha 1, alpha 2, or a1, a2. Does anyone know or guess what the optimal classifier might be? So the best H that actually minimizes this turns out to have a nice parametric form as well. Yes?
Just a guess, but like, would it be some ratio of the alpha?
Yeah. So it will again be a threshold classifier. So it'll be sine of p y equals 1 given x minus some delta. And I'll confess that even though I wrote some of the papers that define this stuff, I don't remember offhand the actual ratio. It is a ratio. It's some ratio of, do you remember? Okay. It's like A1 over A1 plus A2, something like this. Something very close to that. I will refer to a paper. It's actually quite easy to prove for yourself, actually, surprisingly, even though, at least informally, some of the technical details can be hairy, but the high-level proof is straightforward. So this will end up being a useful property. We end up using it a lot for what I'm going to discuss in a little bit. The main point I'm trying to make here is that the optimizer of weighted classification losses looks like a sort of threshold of the classifier of some kind. So if I'm optimizing, if you like, there is a sort of clean connection between weighted losses, threshold of classifiers, and maybe another thing to mention is that you can also think of a weighted loss as a linear function. So I'll just write at the bottom. So any weighted loss, can everyone see roughly? Maybe not. Anyone who needs to see. I assume that the TAs don't, or course fellows don't need to see. Okay, some people cannot see. I'll erase the first one because we're not going to use it. This is a generic statement that will end up being helpful. That so the weighted losses are weighted utilities. So stuff of this type can all be written equivalently as like a linear function of the confusion matrix, but you can also write this as like, a few different ways to write it. You can write it as A transpose C, and then you do a trace. You can also write it as like vectorizing A transpose vectorizing C. So all these are the same thing as sort of weighted utilities all have this form of like linear combinations. And so the connection I'm hoping to make is that if I'm interested in a weighted loss or weighted error thing, all of these end up being solved by some kind of threshold classifier with some threshold somewhere. So how is this useful? It's a bit of a digression. So let me connect. So it turns out that we can actually map out, for all possible classifiers, we can map out sort of all of the achievable confusion matrices. The way that we like to do this, you can do this a bunch of different ways, depending on how your favorite choice of parameterization. It turns out that even for binary matrices, even though they're 4 numbers, they're actually only 2 degrees of freedom. Does anyone know why? You can take a quick look at the confusion matrix. So it turns out you can show this a bunch of different ways, but one easy way to show this is that the sum of TP and Tn have to sum into the probability of y equals 1, which is a population constant. It doesn't depend on anything that you're doing. Similarly, sum over this column sums to some constant. And so independent of the classifier that you pick, even though they're 4 numbers, it's 4 numbers such that these 2 row sums are fixed as something. So you can show that actually they're only 2 degrees of freedom of like the actual flexibility that the classifier has in this setting. It only adjusts, it can adjust the 4 numbers, but you can always, like, if I have 2 numbers in this 4 numbers, I can always work out the other 2. Is that? So if I have any 2 numbers, did I need to? I think so. But for sure, if I have sort of this number, I can always work this out by taking overall fraction and removing that. Will give me this number. Similarly, I can do that for that column. Yeah.
Is it 2 degrees of freedom in the multi-class case also?
In the multi-class case, it is not 2. It is k times k minus 1, I think. I have to double check. But it's not 2. Huh?
It's not 2.
It's not 2, yeah. So it ends up scaling, I think, roughly quadratically with the size of number of classes. Yeah, it's good question.
It's kind of complicated, I think, because there's some issue with like a cusp or something.
With the what?
Like a cusp points.
Yeah. No, that's a whole other, we're not going to get into that.
Like like different.
Yeah, it's the multi-class case can be meaningfully different, and one of the reasons I'm choosing not to discuss it. It gets complicated very quickly, so we just stick with the binary case. Okay, so binary case, we've done some degree of freedom stuff. The main observation here is, I can describe everything with two numbers, and here I'm just choosing to use true positives and true negatives as the two numbers. If you've seen ROC curves before, this is effectively an ROC curve. An ROC curve essentially allows you to show sort of, as I trace out different choices of threshold for a given probability model under some underlying generative model, like overall data distribution, I can trace out sort of all of the possible combinations of true positive, true negative, which are essentially all the feasible kinds of classifications I can build with a particular model for a particular data set. This maps out the whole space. For the problems we care about, we only care about usually the top part of the RLC curve. It turns out you can also map out the bottom part. You have to do a weird thing. You have to intentionally classify badly to do negative classifications, anti-classifications. But if you wanted to map out all possible classifiers, so meaning I look at a classification problem, some data generating model, and I want to map out every possible TP-TN pair that's feasible for a particular model. It turns out that you can fully describe that space. And the nice thing is that the boundaries of that space are given by thresholdings of the conditional probability. So this is a sort of nice property. What this means is that I can sort of tell you, without knowing the detail of whatever function that you're choosing to use, I can tell you all the achievable trade-offs that are available for a particular classification problem. And it just maps out to trying out all possible thresholds for the underlying conditional probability. Yes?
So it's like a Pareto frontier?
So the Pareto frontier. Okay, that's a good way to say it. Maybe a better way to say it. The connection to thresholding will be useful, which is why I'm using it. But it's essentially the Pareto frontier of TP-TN as two objectives.
Across all possible.
At all possible classifiers for a particular data generating distribution. Okay, questions on this?
Is P equal to delta here?
Delta is going to be a good question. The delta is going to be some function of the A's. So put it here, where delta is, I'm going to call it like G function of the A's. If I give you A1 and A2, then I can work out what the delta is, and I'll refer to a paper.
What is P in this case? Pi, sorry.
So pi, this is a good question, thank you. So pi is probability y equals 1. I'm just explicitly mapping out the degrees of freedom. So if you remember on the confusion matrix, I showed the column sums. So probability y equals 1 is pi, and then the only other choice is y equals 0, and probability y equals 0 is just 1 minus the probability y equals 1. So even in the row sums, there's additional lack of degree of freedom. Actually, an important thing.
Is it probability y equals 1 given in X, or just probability y equals 1?
This is marginal over the population, so y equals 1. So P of y equals 1 given X is the full thing. It'll be the object that we're sort of playing with. If I average this over all the possible X's, then I get pi.
In this graph, delta has a rule. In this graph?
Yeah, so I apologize for being lazy because I didn't work out the actual equation. But the delta here, I'll connect it in a second and let me know if it's still confusing. 2 seconds. Okay. But delta has a role to play. So delta is the threshold on the conditional probability model. The claim I was making is that it will map directly to a choice of A. And I'll try to make that connection useful in a second. We'll see if it works. Okay, so the other point I was making, which I already put here, is that so weighted measures works out to linear combinations of the confusion matrix elements. I've already sort of made that claim. And there are a few ways to see this, but I'll just state it as a, what's the best way to say it? Lemma, maybe? You can improve for yourself. If I have a convex space, and I'm looking to maximize something over the convex space, the maxima, if I'm maximizing a linear function over a convex space, maxima always lie on the boundary. Just state that as a statement. The good references in like optimization 101 textbooks, or if I don't think I have a reference in the notes, the references in the papers that I refer to in the notes. So if you take a look at those, or if you ask me offline, I'll send some references. But if you're not familiar with this, if I'm optimizing a linear function over a convex space, the optima is always somewhere in the boundary. And so the intuition we're going to try to use here is that the optima always lie on the boundary. The optima are always going to be these kinds of linear functions. You know that these linear functions are these kind of thresholds of the conditional probability. We're going to try to use that intuition to sort of map out. So the main thing we're going to do here is we're going to reduce the problem. Again, where we started was want to fix an A that matches a stakeholder preference. I forgot. So all of this engineering is such that we can convert this A really into a threshold and show that there's a sort of correspondence one-to-one. And the way that it will help us is that finding the metric that matches stakeholder preferences will boil down to like searching along this boundary. But we turn a, I guess, four-dimensional problem nominally in the confusion matrix space into a two-dimensional problem by exploiting degrees of freedom, into a one-dimensional problem by exploiting the sort of geometry of classification problems. So it makes our life easier, if you like. But the underlying goal is still the same. We want to find some model that matches stakeholder preferences. Questions? Okay, so let me try to put this together. How do we actually do this? It turns out that sort of a reasonable way to do this is to unroll the space. So I want to find a linear classifier, or sorry, a linear metric, so a choice of weights that best aligns with a stakeholder preference. I didn't mention this, but I think it's worth mentioning. Actually, let me actually just state this. So suppose I could do point-wise search. Actually, yeah, okay. Suppose I could do search. What might be a good way to try to find the maximum? Maximum being, I get to ask people questions. Every time I ask the question, they give me some signal. And I want to find, you can either think about this as the point on the boundary that's closest to your preference, which would be essentially finding this delta. Or you can think about it as finding the linear sort of weighting that most matches their preference, which is, again, the sort of, it's A are these relative A1, A2 weights. What might be some good algorithms for solving this problem? It's like a search 101 problem. So again, we're in the noiseless setting. Things are nice and easy. What might I try? Guesses? Have you seen this before? You might have. You should have. If you haven't, that would be boring. Okay, so binary search.
I might as well.
So binary search turns out to be a good, worrying because he's in my group and should have read some of my papers. But, yeah, there's no requirement. It's just an observation. Okay, so binary search turns out to be a good thing. It turns out binary search actually also works if I don't get to see things pointwise, but I only can ask pairwise preference queries. So what I could do is I can ask a bunch of pairwise preference queries along the boundary. I can ask, do you prefer the classifier here versus the classifier here? Because I know how to map from points on the boundary back to linear weightings back to classifications. So I can either ask these in the sort of confusion space or in the classifier space or in the sort of threshold space, depending on whatever makes most sense. If they tell me that they prefer B to A, this suggests that whatever the maximum is, it must be somewhere towards the right. I check B and C. If they also prefer C, then it must be towards the right. This is a particular instance of this set of queries. C and D, what do you prefer? Prefer D, then it must be towards the right. D and E, I prefer D. So wherever the optimal of this thing is, we know that it must be somewhere between D and E. By doing the binary search. Yeah.
Do we know anything about the convexity or concavity?
Yeah. So this is under the assumption. This is a good point. So there is a weak uniqueness assumption that's being made. Roughly. So what you need is you can also connect this to a rationality assumption. I think that's a good point. So meaning there actually exists a utility that is actually driving people's decisions, And there is more than that, there is a utility. So there is a unique utility. Or like we can approximate their preferences well enough with this linear weighting over different errors. So when that breaks, of course, this, at least the like specific approach here will break. So this approach works, that's extremely good points, because for that to work, you need this sort of unimodal thing. And unimodality comes from the fact that, from the claim that there exists a utility within the class of utilities that we're searching over. So it allows us to use a standard search procedure. Very good question.
So capital A is not given that these preferences are constructed using sum A.
So that's an excellent question. So every point I'm querying corresponds to a point on the boundary. Every point on the boundary is equivalently either a choice of threshold or a choice of A or a choice of C. Essentially, they're all equivalent. All of this derivation was to try to anchor that as sort of, and given a problem and sort of distribution, I can connect all these things together. And all of this machinery is exploiting the geometry that comes from that to reduce the search space to one dimension and sort of make these connections, make the search easier, essentially. Yes?
So what you say is a noise-free setting, you mean like when people compare, if they compare several tabs, it's
Yeah.
the same.
Yeah. So that the comparisons actually reflect your true preferences, and they're giving you those preferences without error. So if there is an error, then this is either the Boltzmann setting, there's some noise addition. We'll go through at least one example where you can expand this idea a little bit. You can use a probabilistic variant of this search will work. See, we're slower in time than I imagined because I spent a lot of time on the setup. But I think we'll have time to go through at least one of these examples in the more noisy setting.
Can I just ask one?
Yeah, please.
So like the point on this battery, it's a true positive, a true negative for the population. So say that you want to deploy this thing to some human, you have finite data.
Mm-hmm.
So I was wondering how does a battery have finite data impact? Does it make the battery kind of blurry?
Yeah, that's an excellent point. Yeah. So what will happen with finite data is that instead of having a smooth boundary, you have a sort of stepwise thing. So it ends up looking, and if you've drawn ROC curves, it will look something like this. There are a few ways to fix this. The most common way that people use in sort of ROC literature is just connect these. Because you can show that I can achieve a classifier at the interpolation of sort of the convex hull is achievable. The way you can achieve the convex hull is through a mixture of classifiers. These two will always achieve the ROC of the middle. Or so any point in the interpolation can be achieved by mixing the points on the edges. This is a bit of an aside. Your question was, what happens if I have finite data? The answer is you end up with this stepwise thing. Something like that. You can convert the problem reasonably easily to something where this algorithm does something reasonable.
The curve they don't move back and forth if you have little data. As in like the true positive estimation under finite data. So
that's a source of noise.
Yeah.
Then you want to use a sort of more noise robust search method than pure binary search. Yeah. So all of this for really expository purposes, but also actually even the original version of this work, we got reasonably far assuming noise free and sort of dealing with at least some of these sources of noise that lead to stepwise patterns in ROC space. Okay. So there are some proofs in the paper. I won't go into any detail. The main claim here is direct consequence of binary search. So if I just look at like what guarantees binary search give me for searching in like a nice problem space, it turns out that for a binary search problem, I get epsilon accuracy with log 1 over epsilon steps. So by proof by binary search, I guess is the statement. But again, the details in the paper if you're interested. it also turns out that unless you make more assumptions or constrain the problem further, we are pretty sure this is the lower bound. So you can't be faster than this, meaning there is no way to ask other than making more assumptions or like constraining the problem further. This is the fastest that you can estimate the trade-offs. So you can't, there's no way to ask fewer queries and get higher accuracy in the worst case anyway, on estimating the trade-offs from people. So this connects to, again, the comment earlier, like this is a space where it's sort of constrained enough that we can actually give some quantification of things like query complexity. How many questions do I need to ask to get a good estimate of the sort of individual preference here? Okay. There's a little bit of extra work, adding various kinds of noise. We call people Oracle in this work, so you can use sort of public extensions to handle some of the noise. I'm not going into this. There's a bunch of other papers to look at to handle multi-class settings. I think it asks this question, more complex metrics, and some work and so different kinds of stakeholder group settings. We also did some more applied work. We'll have a whole lecture in HCI, so I might use this example when we go back there. So for time reasons, I'll skip on the details. It's in the slides, and there's a paper as well, where we implemented this idea with some stakeholders and showed that eliciting in this way seemed to better reflect their preferences than some other default approach. Okay, any questions on general framing? So again, big picture, I'm interested in metric selection for classification problems. I'm looking to pick cost-sensitive metrics that align best with like a stakeholder. And what we've done is exploit some of the properties of the classification problem such that we can convert the metric selection problem, particularly in the binary case, to essentially one-dimensional search problem. It allows us to use some off-the-shelf binary search algorithm and make some specific claims in certain settings about how quickly we can pinpoint the weightings that best match the stakeholder preferences.
I guess in terms of like questions to directly ask users, like how do we get something that's a little complex like this? Like, would you prefer?
Yeah. Okay. So this is an excellent question, and in fact, it's one of the big gaps in this line of work. So this framing depends on the ability of the Oracle to do population level comparisons. And so you can think about, in this example, this is like, so I guess one key point is first educating on like perfect classification is not possible. And in general, this is true. If it's not possible, here are different trade-offs that you might imagine making. And what we're trying to ground stakeholders on is how this trade-off might look like in maybe individual examples. So, you know, one of the ways that one could try is like come up with scenarios that capture what this might mean if I, like what a false positive, false negative error might mean, and ask preferences for those situations, and then ask them like how this might reflect in a population level based on a sort of base error rate or something like this, and try to get at their preference from that. I think your point is very well taken. I think that's actually a big gap in this kind of work, is that it needs a fairly sophisticated stakeholder such that they can do these kinds of comparisons, because these comparisons are at a sort of population comparison level. And so some of like useful extensions of this work might include like not specifying the measures at the overall. So, okay. So things are tied in that if you're interested in weighted consensus metrics, the natural space to do the comparison is at this population preference level. If instead, either you think your preferences are much more contextual, so it's not about overall population weights, but like individual example weights, for example, then you want, one, your problem gets more complicated because the set of measures now needs to be conditional. So A will condition on X now, because it's a different way to say it for different points in the space, as opposed to a single weight across all different kinds of errors. There are ways to frame a problem like this. This has the big benefit of like the elicitation problem is a little bit easier because I can now do it as an example level as opposed to population level. I can give an example for this person. Would you prefer this mistake versus other mistake. Right? It's like much granular, easier for response. But then your metric space is much more complicated. We sort of intentionally tried to give queries of this type because we wanted people to, like, their cognitive biases to match the population setting, because otherwise you can actually have a mismatch between the way you're asking the question and the sort of kinds of metrics that you're asking for can lead to other kinds of mistakes and errors. So I guess maybe the big takeaway is, and actually given the questions, and I spent a bit more time on these in the HCI lectures, the useful versions of this usually need some meaningful connection between the algorithmic problem and sort of the human interface problem. It's very important. Okay, other thoughts or questions? Yes.
So it seems like the whole framing, it doesn't necessarily have to be true positive with the rate. It can be anything as long as complex combination and it have only the geometry.
Yeah.
Then like the search and the query complexity can just apply. So for example, I might trade between maybe the cost of I constructing a certain model versus the accuracy, and not necessarily about false positive and false negative.
Yeah, so the question is, I can restate it as like, is this a generic way to do Pareto frontier search, right? To pick operating points in a Pareto frontier? Yes and no. I think the thing that makes this actionable is being able to map back from a choice on a frontier to a particular model that achieves that choice. If you have a mechanism that can do the full loop, then in principle, yes, I guess you can generalize the same idea. This comes out really nicely in the classification setting. I think if you're thinking of, I don't know, that's a complicated one, accuracy versus speed of training. Yeah. Right? And if you have a sort of a good way to instantiate the full loop of this, then in principle, you can use a similar idea. It gets much more complicated in general, though. So this is a case where things work out. I'm not sure. I haven't thought about other cases, but the methodology that is, other than we're exploiting the geometry to make our life easier, I guess it's not that special to necessarily binary classification. Sure.
I mean, the geometry is special.
Yes.
That it's convex and,
yes,
one object. Because
where does the complexity come from? With the fact that you have linear combination?
The convexity comes from, what's the easy way to say this? So I guess the statement is the set of feasible confusion matrices are convex sets.
Well, that is intuitive in the sense that, like, you can argue, like, oh, well, if I have two classifiers...
Yeah, you can always achieve the interpolation, yeah. So you can prove that easily, actually. So let me state that explicitly, just for people who are interested. So the statement, the set of feasible confusion matrices is a convex set, comes, or one way to prove it. The key property of convexity is that taking any 2 points, I can find a point in the middle, any point in interpolation will always be within the set, as you might recall from either machine learning or, so this is the statement. That the key property of a convex set is that any 2 points, you can interpolate and remain within the set. And, if I have a set like that, I can pick 2 points that I have to leave the set to interpolate, and that's not a non-convex set. And so the statement being made now is the proof of convexity for confusion matrices is easy to show because if you know that, if you remember from ROC curves, essentially, that any 2 points in the ROC curve can be interpolated by weighted combinations of the classifiers. That's sort of all you need for that proof. I just wanted to make sure. Go ahead. I hope I didn't lose your train of thought.
No, I mean, when we talk about something like more abstract, so what was it, like training speed and some other metric, I think it becomes less clear, what space that's going to live in. So
yeah.
You might argue oh, well, you can just randomly pick or something, but then it doesn't end up working out the same way because maybe the actual shape that you get isn't interesting.
Yeah, I don't know. So I think the actual answer, I think the premise is appealing, that you can generalize this idea to other things. I think your criticism is also correct, which is, for this to work, you need some of these properties to be true, including convexity of the space over which you're searching, which is what makes the connection easy. And if I wanted to use this from some other setting, we would have to check those properties and see what was true, or devise something that worked in some other space.
This is a comment, no?
Okay.
But I think it's useful. Like, the idea of a confusion space, or trying to tabulate how, or the Pareto frontier idea, any way you want to call it, that is a useful and generalizable idea that you do see. So, like, people often do research that is very close to something like a ROC curve without knowing it. And if you point that out, you can usually spur them to reconsider something from a different perspective, which tends to be helpful.
I agree. That's a good comment.
I guess like maybe in a generic setting, you cannot have a full loop. But I feel like here, because you pick the threshold, that you end up with many choice of model. But in practice, when I feel like you only have few number of models, like 100 models or something, and you don't, like for cost, you can't threshold. Like there's a model that costs $100, there's another model that costs $110. There's nothing in between.
I think, no, I mean, maybe not. I don't know. It also may be that it's a useful abstraction for the search process, even if, so I don't know. I think it's beyond the setting. So the thing that has been worked out is the setting. I think beyond the setting, there is interest. I think we've played a little bit with trying to extend, but I don't think we've done this in full generality necessarily. And we can talk about that offline. So we have 3 minutes, and I had 3 papers, and we got through one. The third one easily can move to mechanism design. Let me spend a couple of minutes on the second one, because I think it's interesting. Because I also don't think we'll have time to go through it later, but I might offline take a look at it. So how do I do this in 2 minutes? Okay. There's a talk and there's a poster, there's a talk, there's a paper. You can take a look. But maybe I'll frame the problem and a little bit of the algorithm, because it borrows a lot from what we just talked about. So I think this will be close. So the naming and the framing is a little bit different, though there's a lot of underlying connections to what we just talked about. It's again in the setting of binary classification problems. And it alludes to a concept in psychology called inverse decision theory, which is a way to frame the idea of some of how we think about inferring other people's preferences is by one way to think about inferring other people's preferences, to think about sort of their underlying preference problem as matching some underlying. I'm gonna do this badly, so I'll actually stop. I'll say this explicitly in a human-machine interaction setting. So the setting that's interesting that I wanted to work on is the machine has some models. So the machine has done this work of estimating conditional probabilities, and I'm looking to find the classifiers. I'm looking to find the decision rule, and I want to do this from a few samples. A little bit different from the previous setting is I'm going to try to do this at the individual sample level. Instead of at the population level. So instead of comparing, tied to your question a little bit, instead of comparing sort of population metrics over, or population performances over things, I'm going to exploit geometry a little bit more to actually try to do search over specific examples and ask people preferences over labelings of different examples as a way to get at, you can either think about this as the threshold that best matches their preferences, and then my claim is this threshold will map to a trade-off in sort of error space that best matches the trade-offs that they're most interested in. So again, like much of what we've been doing, you need, I didn't mention this earlier, but actually this is a useful abstraction. You need the model first for both of what I've talked about. You can think about this as one abstraction that people sometimes like is think of getting this model as pre-training, right? Getting the overall distribution, and then preference tuning is finding the weights or the threshold that matches the decision-making setting that you're most interested in. That matches a little bit some of the rest of the settings that we've been talking about. Okay, so So what's helpful to say? So it turns out I can solve this problem. I think I'll just go straight to algorithm. So it turns out I can solve this problem. I think the interesting aspect of this paper compared to what I just talked about is that we tried to be a bit more explicit about sources of noise, as opposed to, again, assuming zero noise. So this allows for noise that comes from a distribution of stakeholders, noise that comes from some extent error in the algorithm, potentially, other kinds of noise that can lead to uncertainty. And the main algorithmic change here is that using a probabilistic version of sort of a search algorithm instead of the deterministic one. So you can use a probabilistic bisection algorithm, details in the paper, or in the slide and also in the paper. Works very similarly to what we just talked about. The main difference is, again, it allows for some uncertainty. The key intuition is you build a prior over possible threshold points, and then every time you get additional signal, so labels from people, you upweight evidence that's telling you the threshold is more likely to be here or not here. And in fact, you can use this to show explicit proofs of like how long will it take before I get the right threshold. And you can think about this as when will the measure around a particular point be high enough? So greater than half, for instance. So I won't go into detail, but mention this is there. I'm going to end here because we're at time. I think the thing, and we'll talk about options when we talk about mechanism design. Maybe I'll just go straight to summary. So I'll just move this to future lecture. So the main things we talked about metric elicitation, which is a specific instantiation of the combination of preference estimation and the sort of classification problem, and showed that you can do sort of some special things there because there's a lot of structure that you can exploit. And we talked about how we can use this for some of the aggregation. I did this very quickly, but this is the second paper. I may try to find time to spend more time on that because I think it's interesting. We didn't talk about this, but I'll mention you can use this for other kinds of problem settings like algorithmic fairness problems and the like. And we didn't cover the last one at all. So that's most of what I wanted to cover today. I think it's fine that we mostly covered the main thing because the key intuition is, again, and the key takeaway, well, one is, just like in general learning problems, we spent a lot of time thinking about utility functions and metrics. Even in very simple, say, binary classification problems, that choice is also an important one. And many of the tools we've been building over class can be useful there. And specifically in that setting, we can use this combination of active learning and preference learning as a way to do a, hopefully, much better job of picking utilities that better reflect stakeholder preferences. And so that's the key takeaway, hopefully, that I'd like from this. And some detail in the slides and maybe in homework to ground some things. And in future lecture, we'll talk about bandits and sort of other kinds of algorithmic tools that can help us in preference learning. Thank you.